Hi, this is Isaac Schaefer, and this is my third video presentation for Math 431. Today we're going to work on problem 10.3, where we're asked to solve by means of the sine or cosine Fourier transform this initial boundary value problem, where we're given that the boundary condition at x equals 0 is insulated, that is, that the derivative of the temperature profile with respect to x is equal to 0, and then an initial condition which is actually equal to the Heaviside function, where the Heaviside function in this case, it tells us that the temperature is going to be 1 between 0 and 1, and otherwise 0. Finally, after we have a solution, we're asked to graph the solution for various time values. Before we begin solving the problem, it helps to think about what the boundary condition and initial conditions are telling us about the final solution. First, since the boundary condition tells us that u sub x equals 0, this means that the boundaries are insulated along at x equals 0 and along the lateral boundaries. So what this translates to is that, number one, the slope of the temperature profile is going to be 0 at x equals 0 for all time t. Next, it's also going to tell us that the energy, the change in energy, is going to be 0 for all time t. It is that no heat's going to leave the system. But because these boundaries are infinite, that is, that the x goes off into infinity, what's going to happen is that energy is going to keep spreading out through diffusion forever. And eventually, it's going to probably do some kind of like, its limiting value is going to be something like it's going to just be 0 everywhere, but at the same time, the energy is not going to be different. It's like everything, the heat's just going to spread out infinitely wide and far from each other. It's kind of a weird idea, but I think that's actually what that means. Secondly, because the initial condition has a discontinuity at time t equals 0, the instant after t equals 0, there's going to be this like unrealistic, unphysically realistic, or I should say unrealistic jump in temperature. Like this isn't just go instantly from 0 degrees to 1 degree. And so the solution doesn't have a real physical interpretation. However, the initial condition also has some interesting behaviors at the boundary. So initially, after that jump, what's going to happen is that diffusion will only occur at the edge where the temperature difference actually exists. But the internal points of that, where it's still 1 degree, it's going to remain constant until that kind of like that energy is burned off like a candle over time. And this is because if you think about it, like the concavity is going to be 0 because the average of the temperatures near any point on those in the interior of that interval are going to be 0, or the average and the temperature at a point are going to be the same. Therefore, the concavity is going to be 0. And that's what we learned from lesson 2, where we had that the temperature concavity is approximately equal to 2 divided by the delta x squared times the average temperature near a point minus the temperature at a point. And so we should expect that our actual final solution will have this behavior, at least initially. And since we're also asked to use either a sine or cosine transform, we're going to have to pick one that is most useful for us given our problem. Now, since that u sub x equals 0 is our boundary condition, we want to choose a transform that allows us to make use of that. And so the best one here would be the cosine transform, and that is because of the derivative, the fourth derivative property, where we have the Fourier cosine transform of f double prime is equal to -2 divided by pi times f prime at 0. And this translates actually to that f double prime in our problem set would be that the u double x, right? And then over here that u prime, then the f prime, would be our u sub x. And since we know what u sub x at 0 is, this is actually the best candidate because we don't really have a way to use it anywhere else with any of the other properties. And so now that we know what we're going to use, we'll move on to the next step, which is where we transform the PDE, boundary condition, and initial condition using the Fourier cosine transform. First, we're going to assume that the transform is equal to a function u, which is a function of variables omega and t. Then we're going to apply the cosine transform to u sub t. And notice that while we use the definition, we use the definition of the Fourier transform, but then we can actually pull out that differential operator, that partial of that where we can differentiate with the partial of t, with respect to t. Then now the internal integral becomes actually the Fourier cosine transfer of u. And since we define that to be big U, we can then use that, substitute that assumption. And then because we don't actually need to worry about omega, and we can treat it as a constant for the rest of the problem, we can then assume that this is now a normal, ordinary, I should say, differential equation. Next, we'll transform the concavity using the cosine transform. And since as we already discussed, what we have here is that we're going to substitute our u sub x at x equals 0, which equals 0. And then we'll apply our Fourier transform of u. But we don't know that, but we can use our assumption, which means that we're going to set that Fourier transform to u. And then this all simplifies to negative omega squared times u. And therefore, the PDE transforms into an ODE. That is, it's where we have the derivative of u, the time derivative of u, is equal to the negative omega squared times alpha squared times u. The initial condition is transformed again by the cosine function, or the cosine transform, which is really just us transforming the Heaviside function and then applying the definition of the transform gives us this integral, gives us the integral of 2 pi of h of 1 minus x times the cosine of omega x dx when we integrate from 0 to infinity. And since the Heaviside function is just 1 between 0 and 1, and then 0 everywhere else, we'll separate out the integral, since it's linear, of those two parts, and then we integrate. And this gives us this initial condition of 2 divided by omega times pi times the sine of omega. Now, this next step, we're going to solve the resulting ODE and initial value problem. And so, since this ODE is really just a first order homogeneous differential equation, that means that all we have to do is find a characteristic equation, which is r plus omega squared times alpha squared, solve that for r, and then substitute that r for our solution, since in an exponential function, which in this case is u of t is equal to some constant c times the exponential function raised to negative omega squared times alpha squared times t. Next, we apply the initial condition. So, since in the initial condition at t equals 0, what we can do is then plug that into the general solution of c times the exponential raised to the negative omega squared times alpha squared times 0, which simplifies to 1, and then set that equal, of course, to our initial condition we solved previously. And since that exponential becomes 1, that just means that c is equal to the initial condition. And therefore, the initial value problem solution is u of t is equal to the 2 times the sine of omega divided by omega times pi, and then that's all times by the exponential raised to that negative omega squared times alpha squared times t, which is a big mouthful. All right, now we're going to apply the inverse cosine transform to the solution of our IVP. And that will then give us the solution to our original initial boundary value problem. And so u of x of t is equal to the inverse Fourier cosine transform of big U. We apply the definition of the inverse transform, which is that integral between 0, where we integrate our solution u times cosine of omega x from 0 to infinity, and we integrate with respect to omega. Then we substitute in our solution to that from that IVP. Then we simplify things a bit and then integrate. And what we arrive with is a function of the error function. Or I should say it's a little awkward, but we arrive at the error function. It's just the term, two terms of the error function. All right, we're almost there. So now we're going to talk about the graphs of the solution for various times t. From the top left corner, we have the Heaviside function at t equals 0. And then as we predicted in our interpretation, there's going to be a kind of melt-off where the heat flows out at that edge of that initial condition and that shrinking interval and starts flowing towards the higher x values. And then eventually reaches a point where everything is actually now less than 1 degree Celsius. And at that point, what we see is that at x equals 0, everything starts to shrink. But at the same time, we still maintain that 0 slope at x equals 0, as we predicted. Now, as we progress downwards, or progress through time, what we see is that right about the point we hit 0.5 degrees Celsius, there's a very noticeable slowdown in diffusion. And that as we progress from that point, that middle central graph, everything starts to slow down. And up until that point, we're at about maybe 5-ish seconds, if that. And then after that point, it actually starts growing quite a bit. So like right around that last middle graph there, that's probably about t equals 10. And then by those last two graphs, actually what we have is that t equals 100 and t equals 200. It's a minor point, but it just noticed that, it did slow down quite a bit. Another thing to notice is that it does seem to be that the temperature is just all going down to 0. And it kind of makes sense in a way, the way that the system was set up originally, that would happen. Now, at the same time, it's kind of strange that the temperature will be 0 everywhere, but the energy isn't going to change. And so while the limiting behavior is that it goes to 0, but it will never actually reach 0 unless it's how infinity and limits work, right? But anyways, there's something interesting to think about. So, all right, that's it. That's the problem, and thanks for watching. All right, bye.